Good afternoon, one and all. Myself, Pravin Vadhel, lecturer in mathematics from V.V.P Engineering College, Rajkot. Today I am going to deliver a lecture on indeterminate form. That is my chapter name. So let us start with the indeterminate form. In indeterminate form, before starting indeterminate form, let us see the outline of the chapter. This chapter contains, first of all, we will discuss some historical background of chapter, then its definition, that is the definition of indeterminate form, then L'Hospital rules of the form 0 by 0, then working rule, how L'Hospital rule works for the given function, then example of the form 0 by 0, then L'Hospital rule for infinity by infinity and its example, then again L'Hospital rule for 0 into infinity form and its example, then L'Hospital rule for infinity by infinity form and its example, and finally we will see the L'Hospital rule of the form 0 by 0 raised to 0, 1 raised to 1 raised to infinity, infinity raised to 0 and its example. So let us start with the historical background. John Bernoulli, the name of the scientist who has discovered the calculation of a limit of fraction functions, in which when we substitute the limit, both numerator and denominator will approach either 0 by 0 or infinity by infinity form. Today we know this form as an L'Hospital rule. So this is the picture of John Bernoulli, and this rule is nowadays known as L'Hospital rule behind the L'Hospitals, who was a French nobleman, and he has also written an introductory differential calculus text where this rule first came in print. So let us start with the definition. So it is not easy task to study of limit of sum, difference, product and quotient of two functions of the following type. First type is, if any quotient function we will take fx upon gx when x tends to a. If fx tends to 0 and gx is also tends to 0, then we have 0 by 0 form. If limit x tends to a, fx tends to infinity and gx tends to infinity, then we have infinity by infinity form. Now we consider the product of two functions at x tends to a. If one function is equal to 0 and another function tends to infinity as x tends to a, then we have 0 into infinity form. Then next is the subtraction of two functions. Limit x tends to a, if both functions approaches to infinity, then we have an infinity minus infinity indeterminate form. Then if at x tends to a, now we are taking the function raised to the power function, in which if one function for the given limit is equal to 0 and another function for the given limit tends to infinity, approaches infinity, then it will be 1 raised to infinity form. Then next is limit x tends to a fx raised to the power gx, it is again the same kind of function where the limit fx is equal to 0 at x tends to a and gx is also 0, then we have a 0 raised to 0 form. Then finally limit x tends to a fx raised to the power gx, if fx tends to infinity and gx is equal to 0, then we have infinity raised to 0 form. So these are the functions that we have seen in which we cannot find limit at a given limit point which leads to some undetermined form like 0 by 0, infinity by infinity, 0 into infinity, infinity minus infinity, 0 raised to 0, 1 raised to infinity and infinity raised to 0. So that's why still it is undefined, and that's why these all forms are called as an indeterminate form. Now the question of evaluation of such kind of limit, especially if we talk about 0 by 0 or infinity by infinity, then it is possible with the help of one rule. That rule is known as L'Hospital rule, and which is also referred as Cauchy's rule. And the other rest of the forms except 0 by 0 and infinity by infinity can be reduced either into 0 by 0 or infinity by infinity form by using some suitable arrangement, or we can say algebraic operations. So these are the types of indeterminate form that we have to cover in this chapter. So let us begin with the first type of indeterminate form, that is the L'Hospital rule of 0 by 0 form. Now let fx and gx be any two differentiable function on some open interval I which contain a. If limit x tends to a, fx upon gx leads to the indeterminate form 0 by 0, that is when x tends to a, f of a and g of a both approaches to 0, then we have this kind of situation. Then limit x tends to a, fx upon gx is equal to limit x tends to a, f dash of x upon g dash of x, provided the latter limit exists. Now one corollary, that this is the part that we have to find the limit in this way by differentiating numerator and denominator, and then we get the limit of a given function. But if consider we have some functions in which all the n minus 1 derivatives are 0 but nth derivative of the given function are not 0, then we have this kind of situation that we have mentioned over here as a part of corollary, that is this. Now next is working rule. So in working rule we will see how to apply L'Hospital rule on such kind of functions which leads to an indeterminate form of the type 0 by 0 or infinity by infinity, how it works on the given function. So for finding the limit of such function, we have to apply L'Hospital rule, or we can say that L'Hospital rule works on it in this way. We have to differentiate numerator and denominator separately, then put limit on it, whatever the given limit is there. If again function reduces to indeterminate form of our given type, that is 0 by 0 or infinity by infinity, then again we have to differentiate numerator and denominator separately. We have to continue this process until we do not have some finite limit value. That is, the rule is over here, as I have told you. So in this way, L'Hospital rule works for the given function which leads to an indeterminate form 0 by 0 or infinity by infinity. One more thing I would like to share, that is, specially L'Hospital rule is defined for 0 by 0 and infinity by infinity, and the rest of the forms we will convert either into 0 by 0 or infinity by infinity form by making suitable algebraic operations. Now the next is example of the form 0 by 0. The first example, evaluate the following using L'Hospital rule. Limit x tends to 0, 3x minus sin x upon x. So here two functions are given. At x tends to 0 we have to evaluate. The functions is 3x minus sin x upon x. So on substituting x is equal to 0 in a given function, we will get 0 by 0 form. As I am substituting x is equal to 0 on numerator and denominator, I will have 0 by 0 form. So as we have studied about L'Hospital rule, we can apply L'Hospital rule over here. That is, we have to find the derivative of numerator and denominator separately. So derivative of 3x minus sin x upon x is 3 minus cos x upon 1. Now again put x is equal to 0 according to the working rule of L'Hospital. That is, if we put x is equal to 0, then we do not get 0 by 0 form. So we can find the limit. So I am going to apply the limit on it, and the limit as we have applied, it is 3 minus cos x by 1. As x is equal to 0, the answer is 2. That is the finite value for the given function. Now let us see one more example, but before it, sometimes it may happen that for the given function it is very easy to find the limit for the given limit point by using cancellation or rearrangement of steps, or by using some algebraic manipulation. We will consider this kind of example over here also, that we have to apply L'Hospital rule finite times, or we can say that 1 or 2 times. Let us see the next sum. Now next sum is limit a tends to b, a raised to the power b minus b raised to the power a upon a raised to the power a minus b raised to the power b. Now here our variable is a, and now a tends to b. So as you substitute a is equal to b in the given function, you will again get a 0 by 0 form. Let us see. So it is 0 by 0 form. So again by L'Hospital rule we have to differentiate the numerator and denominator separately. That is, the derivation of a raised to the power b is b into a raised to b minus 1 minus derivation of b raised to the power a will be b raised to the power a into log b, and in denominator a raised to the power a will be differentiate as a raised to the power a into 1 plus log a minus b raised to the power b will be 0. As I have substitute here, provide a reason which formula I have used here for the derivation, that is a raised to the power x and a x raised to the power x. Now you can see that if you put a is equal to b, then it will not be a 0 by 0 form. So we can find a limit. So as substituting a is equal to b, we will have this step, that is b into b raised to b minus 1 minus b raised to b into log b upon b raised to b into 1 plus log b. Now here in numerator 1b will be cancel out, then we will take out b raised to b as a common, and b raised to b will be cancelled from numerator and denominator, and final answer will be 1 minus log b upon 1 plus log b. Again, next example, as I have told you that sometimes we can also use or also find the limit by using some algebraic manipulation or algebraic operation to reduce the sum or to reduce the lengthy work. Even also we can directly apply the L'Hospital rule of the given function, which leads to an indeterminate form 0 by 0. But sometimes it may happen that if denominators have more than 2 functions which are in multiplication and which occurs in our standard formula of limit like sine, tan and all, then we can use such kind of thing. So this example will be given as using this remark. Let us see. Next sum is limit x tends to 0 sine square x minus x square upon x square into sine square x. Now it is clear to you that when you put x is equal to 0, it will be a 0 by 0 form. So ultimately you can promptly you will apply L'Hospital rule. But here I am not going to use L'Hospital rule directly. As I have told you, I am using here some of the algebraic operation to reduce the given function. So I am going to multiply and divide by x square. Then I have rearranged the term, that is limit x tends to 0 sine square x minus x square upon x raised to the power 4 into x square